So, hello, everyone. I'm Roy Shamir. I'm the co-chair of the New York section of the Audio Engineering Society. Thank you, everyone, for being here today and attending another one of our awesome in-person events, if I do say so myself. Special thanks to our hosts, Post Lab 1, amazing facility here in New York City on 27th Street. Come check them out. Today we're presenting Professor Jill Linz and her groundbreaking concept, AtomTones. Looking forward to that. We'll be starting in one moment. I just want to let everyone know that we have another event coming up on the 22nd, which will be hosted at VoxPod Buttons, New York, presenting Saturday Night Live, 50 Years of Audio, Then and Now. We'll be holding a raffle at the end of this event. I want to thank Eventide Audio for providing the Split EQ and Anthology bundle as prizes for our lucky winners today. So without further ado, let's all welcome Professor Jill Linz and AtomTones. All right.
Woo! Well, thank you. I'm really excited to be here, talk about my project that has been actually 30-some years in the making, and so I hope you enjoy what I have to say about it. Okay, so this is a very interdisciplinary project. In addition to being a crossover between the science or the physics and the music, within the physics, it also incorporates a bunch of different areas, including acoustics, optics, quantum mechanics, and spectroscopy. And so in physics, we really only know one problem. Okay, and I do have up there is that pesky little particle problem. In the physics world, it's particle people versus wave people, and I'm obviously a wave person. But what I have up here is different equations. Now, I know I'm not going to get into a lot of mathematical where you're plugging numbers in. We don't use equations in math that way. It's more of our language. And so really what I tend to do is translate between the equations, the mathematical language, and the music, the language of the music. And so what I have here are 4 different areas of physics. So the quantum particle in a box is really describing how the electron reacts in a hydrogen atom. And that is the exact same mathematics as does standing waves on a string. So when you pluck a string, the way that the waves vibrate follow the exact same mathematics. So it does it in optics. So when we think about color, that is really the same exact mathematics that we're using. And then, of course, acoustic waves, right? When a sound wave travels in air, it also follows the exact same mathematics. This allows us to translate from one to the other. So we can send a sound wave into a microphone that will change it into an alternating current that we can then manipulate. And then we can send that to a speaker, which goes back into a sound wave. And so that's just the basic idea of it. All of these start with the same thing. They start with a oscillation. And so here, this is actually a little video that I had done for another talk with the Acoustical Society. And this is actually just showing the mass and springs kind of vibrating. I'm changing the frequency in this video, but it gives you the idea of the mass moving up and down, up and down. And that's an image that I want kind of burned into your brain, because when you think of an oscillation, that's really what we're talking about, whether it is a physical mass in a spring or it's an air particle that is moving back and forth and banging into other air particles as the sound wave travels through. And so all oscillations follow at their the very minimum is this graph that I'm showing here, this up and down. So those little boxes represent the mass as it's moving up and down in time. And that has an equation. Now, again, this is not something we're going to take numbers and plug into like you think of in math class. This is really our language, and this is expressing what an oscillation is from that mathematical language. So when you look at that equation, you break it down, right? So really the letters in there, those variables, tell us something about the system. And so if I'm talking about light, the amplitude A is talking about how bright the light is. But if I'm talking about sound, it is the volume, how loud or how soft it is. And then with electricity, the current, it's really telling you about the current, the signal, how high is the amplitude in the signal. The frequency, I'm using omega here. Sometimes you might see it as F for the frequency. Those are just different unit systems. The computer does not like frequency in hertz. We talk about frequency in terms of hertz, but if I'm actually coding it in the computer, I better be using omega because it needs it in those units. So most of what I'm having here is in terms of omega. Just a little heads up on that. Okay, so the frequency, if I'm talking about light, again, I'm talking about the color. So red light has one frequency, that's a low frequency, and blue light is a high frequency. Sound is going to be our note or our pitch that we're talking about. And then the phase, that phase factor in there, that governs how the sound waves or the light waves combine together to create what we actually see and interpret. Okay, so oscillations come in many, many forms. So we just saw the springs, right, with the spring just kind of bouncing up and down, but we also have things like molecular and atomic bonds. So the way that atoms combine together to form a molecule, they actually vibrate. Everything is always moving, and they move exactly like a mass in a spring. When I was in grad school, I actually used the exact same equations to mimic how light and matter interacted. All right. And so electromagnetic waves are another one. So electromagnetic waves would cover things like all of our color, right? Our color vision that we see. But it also covers things like microwaves and radio waves. And then on the other end, X-rays, gamma rays, that kind of thing. All of those are electromagnetic waves. And they all follow the exact same mathematics. Okay. And then, of course, we have sound, right, which follows the same mathematics as well. And electrons in an alternating current. And I have the little water waves here because water waves and earthquakes follow exactly the same thing, too, which I find really fascinating. So what I have here is what we think about as color. So, remember the neon lights on Broadway that don't exist anymore? Or I don't know, are there any left? But when we see neon, right, neon has to be red, okay? When I see something like hydrogen, it gives this magenta color. And then mercury has this pale blue. Those are not colors that are nature, part of nature. They have to be a combination of different colors or different wavelengths in order to make that color. And the same thing on the other side here. These are just kind of swatches that are what we would call subtractive mixing of these waveforms of color. And you can see here it has a red tone, so the waveform that it forms, it is not a pure sine wave, it is not a pure oscillation, but it's a mixture of them, right? And so the same way with the green and the blue. Okay. All right, so if I look at just the hydrogen light and that magenta color, that doesn't, magenta doesn't naturally appear. You don't look at a rainbow and see magenta. But it is the combination of different wavelengths from the rainbow that are entering our eye. And so that spectra that you see on the bottom there, that is what scientists use to identify different materials. So when they look into space and they say that star is made out of hydrogen, they're looking at these spectra like this. They actually look at what we call absorption spectra, but it's the same thing, same idea. And so we can identify what the atom is just by looking at these spectra. And it's very easy to do. You can just take what we call a grating, kind of like a very fine screen, and put it over either a camera lens or your eye, and you can see these lines. It's really simple to do. And so I have it here on a spectrum graph with frequency. to just kind of show how I'm going to map these out, right? Okay, so instruments and sound does exactly the same thing as light does. So if I consider 3 instruments, so here I have 3 conical winds. I happen to have the material at hand because I did a big study on this, but it's the shape and the length that is going to determine the pitch of these. And so we know that 3 instruments are going to sound different. If I look at their waveforms and their spectra, so down here at the bottom is their spectrum. This is the different waves, sine waves that are added together to create that unique tone. All complex waves can be broken down into a series of sine waves that we can identify what the material is. We can identify what instrument made it. Okay, and so you can, so that's the horn, right? There's the bassoon, and there's the oboe. And so you can see these spectrum. So the oboe and the bassoon and the French horn are very similar. They're both producing the same note. We would identify that as G3. But you can see that the timbre of the instrument is shown in these different sine waves that come after it, the different harmonics that appear in that. Okay, this is a periodic table of spectra. So that thing that I showed you, the spectrum that I showed you for hydrogen, there is one of those for every single element, or at least the ones that are naturally occurring anyway. There are a few, you'll see it down at the bottom here, there's no spectrum. That is because they were made in a laboratory and they decay really, really fast, and we can't get a spectrum from them. All right, so I've been working on with both of these things for a very long time, and at some point I made the connection that I could translate them from one to the other. Okay, so I started making the tones. Now, I'm using what is known as Fourier's theorem, which says that all complex waves can be recreated by adding together enough sine waves with the correct frequency and amplitude. So just the way that I add them together is going to give me different timbres. And so these are just the mathematical equations. I don't plug into these. I put these into a program. Generally, well, it depends on what I'm doing with it, but Mathematica or MATLAB or Python or something like that. And then, so I took, basically what I did here to do this was to take the spectrum and I overlaid it with a mapping from the wavelength of the light, because we tend to refer to the colors by their wavelengths, and we refer to sounds by their frequencies. These are related by this equation. And so that V is the velocity of the wave, which is constant. So I don't know if you guys ever, for light, it's 3 times 10 to the 8 meters per second, and for sound, it's 343 meters per second. I only think in meters per second. So we just made a mapping just like you would on a regular map, right? If you look at a regular map, they always have a legend in the bottom that says 1 inch equals a mile or whatever their scale is. It's the same idea. I'm taking the scale here and I'm saying there are 3.33 hertz for every nanometer. And so that's just all that I did. When we were first doing this way back, we were actually trying to map it out, like measuring it. And I was like, no, that's not going to work. So we ended up, actually, most of this was done in Max. I don't know if anybody knows Max, but that's where most of this was done in. Okay, so this is an example of the data that we use. So I use the National Institute of Standards, and you can go on there and get all of this data. It's just there for the taking. I chose iron because iron has so many lines that it's showing there. If you're working in spectroscopy, or if you're usually like astrophysics and you want to identify what a particular element is in a star, you're not going to identify it by every single line. You don't need every line. You only need the brightest and the sharpest lines. So we minimize what lines are going to be used to identify this. And I use the same criteria in creating the tones that they use in identifying the different elements in scientific research. Even with that, I still have quite a few lines that I had to deal with. And so I just kind of arranged this a little bit. I just wanted to show you that each one of these, and I don't know if you can see it as well, it's not as clear on my screen, but each one of these are sine waves. They are just single frequency tones. The only thing I'm varying is the frequency and the amplitude of each one. And then I'm just adding them together, right? I'm just bouncing it to a new file. And that's all I had to do. Okay, so when I first did it, and I think my tones are going to be backwards here, but when I first did it, I did it as a raw sound. So this is kind of the basis of sonification. I don't know, it's kind of one of these up-and-coming terms that are being used for the act of creating sounds from non-audible data. And most of the people who do this just kind of throw them together and come up with this really nasty sounding noise. And I made the connection. I said, you know, when we hear sound, it doesn't live forever, right? It decays immediately, depending on what your environment is. And so I put on a decay on there. So this is iron with a decay. Okay. And then this is what it sounded like before I put the decay on. You want to listen to that for a long time, I'm sure. All right. So when I put them together, so here's a couple. I have carbon and oxygen here. And what's really cool here is when I take the spectrum from the sound, so the black lines are the spectrum that is produced by the sound itself. And then I have the actual spectrum that I could get from the National Institute of Standards. And so they are matching up almost identically on here. Okay, and so that's what carbon sounds like. And there's oxygen, all right? Whoop, it's going to do it again. Sorry. All right, so there are 100 of them, and I couldn't necessarily get them all onto the PowerPoint. I'm going to try to do this, and hopefully I don't mess it up. This is on my website. This is AtomTones.com, and every one of these, if you just click on them, you get the tone, and I'm just randomly hitting in on things here. But every one of those tones has a unique sound, and I'll talk about it in a minute. But they also have a unique scale system that will come along with it, which is very cool. Okay, I need to get back. Ooh. Okay. I think I'm there. Yay. Did I get it? Yep. Okay. So I wanted to give an example of just how, like, maybe scientifically something would be used for this with just the elements themselves. And so I found this is a nuclear decay chain. So you guys have all heard of uranium, right? It's very radioactive. And as it decays, it turns into different elements. And so what I have here are the different elements in that chain. So it will decay and decay and decay until it becomes lead. And when it's lead, it becomes stable. All right, so I want you to listen to the way that it starts off with uranium. I'll talk about what they are, but. Okay, so if you noticed, as it started out, it was very rough, very noisy. And as you got closer and closer, it became into a purer and purer sine wave. Oh, I'll go. It's going to play all the way through again on me. All right, It's not going to play again, I hope. So here I have the first three that we're showing here. And so it starts off with uranium. And uranium, if you look at it closely, it almost looks like an AM radio signal. You have a sine wave, that perfect sine wave, within a very noisy signal. But then when that decays, it goes into almost pure white noise. So if you look at the spectrum, so the spectrum of uranium is kind of clustered around the higher end. I limited it to 1,000 hertz. That was what my choice was when I did this. But you can see that thorium, which is the next one, has almost an equal distribution of the sine waves that we've added together. And so that when you have an equal distribution, that comes across as white noise. Right. And then once it starts to decay again, the next one is radium. That was the one Marie Curie was playing around with. Highly radioactive, but the waveform is starting to level out. There's starting to be a little bit of structure in here. And as it goes further, it goes into radon. Now, radon goes back into that, what I like to call the AM radio signal, right? You have that high pitch single tone with other waves adding into it. And then when it goes into polonium, which is the next one, it starts showing almost a beating action. And actually, I even went in and did some measurements in there, and it's showing there are two tones in there that are 5 hertz apart, and that beating action is exactly at 5 hertz, which is pretty cool. And then when it goes into lead, which is the bottom one, if you look at that and if you go really close in, see, I want to look back at it. When you look at it really closely, it goes into almost an exact single frequency tone. There is a tiny little bit over here, and so you see some wavering in the waveform there, but it is almost a pure sine wave, which is kind of cool. I don't know what it means. I just looked at it and said, oh, look how cool that looks. All right, these are the decay rates that they each of these have, and you can see that they all have these half-lives that they have, and then it gets to lead, and there's no decay, which I thought was really cool. Okay, I want to talk about another aspect of this project, and that is with granular synthesis. Granular is my baby. I have been working on granular synthesis probably for 30 plus years, probably closer to 35 years. But it's really rooted in quantum mechanics and the Heisenberg uncertainty principle. So if you see a model of an atom, very often what they do is they make it into a planetary looking thing. You have a nucleus and then they have the electrons whirling around, but that's not a real picture of it. In reality, the electrons are in a cloud that surrounds the nucleus, and they're vibrating. It's like almost breathing, right? And so it's going to vibrate, and that vibration is what we are referring to with the oscillations. So Heisenberg's uncertainty principle says that for electrons, we know where the electron is, or we know how fast it's going. Well, that's like a weird way of, what does that actually mean? This is like a strange way of looking at it, but I always tell my students, if you wave your hand in front, if you wanted to know how fast your fingers were moving up and down, that's a fairly easy measurement to make. You can use a motion detector. We have very simple devices that would measure how fast your velocity is going. But you don't have any idea where your fingers are when they're moving up and down, because you can see them all simultaneously. The only way you know where your fingers are is to stop your hand from waving. And so that's kind of the idea of that, right? But we don't know. So the idea here is that we know where something is, or we know how fast it's moving. We can't know both. All right, sound is a victim of its own uncertainty. If we understand how a waveform evolves in time, we have no idea what its spectral distribution is. We have no idea what the frequency is just by looking at the waveform. But if we look at its spectrum, we can tell exactly what the pitch is and the timbre, and we can actually backtrack and tell what made that sound. Right? Okay, so in order to see the whole sound, we have to consider both of these simultaneously. And so this started back in 1947 when they were talking about this. But what you're seeing here is kind of how do we measure this? If I wanted to measure the wavelength, okay, the first picture here, I have a large measurement. So I'm measuring something that is, 10 meters across, and I can measure the different wavelengths and average them out. But if I have a small measurement, if I only measure a fraction of that, I am only guessing as to what the wavelength is. Okay, what does that mean in terms of sound? It means that if I have a sound that exists for a very short time period, that means that I have a very large bandwidth. So I'm going to have many frequencies. So this graph is showing, I didn't put any numbers in here, but I could have, from maybe like 100 hertz up to 1,000 hertz in here. And every one of those frequencies are going to exist simultaneously, and we won't be able to tell one from the other. Whereas if I have a very large time for the sound to exist, then I'm going to have a very small bandwidth, and I will be able to identify what the pitch is. Okay, so turning the theory into sound. So we create grains, and those grains exist for a very short amount of time. We're talking 5 to 50 milliseconds, and usually it's in the 10 to 25 millisecond range. And we create this sound that only lasts for a very short time and then string them together, one right after the other. And that creates a cloud. Okay, so I just have this, I had this from a different slide, but these are the different controls within any type of plugin that you will have that does granular. But this is an example. We took it from very basic mathematics, and this is a student did this. Is it going to start? Yep. And so what we did here was just vary the different controls. Okay, I'm not going to make you listen to the whole thing.
Was that recorded from a record?
Huh?
Was that recorded from a...
No, we did that through the mathematics. Yeah. And so that was really, we did that so that we could demonstrate granular synthesis and how we're going to use it in terms of atom music, AtomTones. Okay, so now we want to think about the music. And here I want to talk about a little bit about music theory from a physical scale perspective, and then how we developed atom scales. And from that, I'll talk about some of the music that we've done with this. Okay, so Pythagoras was famous for having discovered the relationship between different lengths of string, or he actually started with different metal bars that he had made. There is a story that he was a cult leader would be the best way to describe it. He took all of his followers and they went and lived in a compound. And it was one of these things where you had to give up your worldly goods in order to go study with him. And, but anyway, they had like a whole little town, and they had a blacksmith shop in there. And he was famous for walking around the little town and They say he was on the spectrum, so he kind of would talk to himself and wander around and listen. And he was walking by the blacksmith shop, and he heard the two blacksmiths in there simultaneously happen to hit their anvils at the same time. And the sound sounded pleasant to him. And he became fascinated with this, that he spent the rest of his life trying to understand why that was. And so he had them make a bunch of lengths of metal, and he would go around and hit them, and he hit them simultaneously. Now, he had them all different sizes. He didn't have just the ones that I'm about to show you, but what he found is if he struck a length L, so if he had a 1 meter long bar and then struck it at the same time with a 0.5 meter long bar, he would hear an octave. Well, that's what he called it. And that's actually the term he actually used, which a lot of these are not the same words, obviously, but octave has held through. If he struck with L over 2 with L over 3, so just divided that length by 3, that is what we call a perfect fifth. So that ratio is 3 to 2 or 1.5. And then if you did it with L over 4 and L over 3, you got a perfect fourth. Now, of course, they knew of major and minor thirds in those days. They had stringed instruments. They were tunable. But he couldn't make the strings or the bars short enough to be able to really do any type of experimentation with it. So his entire system was actually done with the octave, the fifth, and the fourth. Okay, this led to the development of just intonation and the basis of our music theory. And so it's all based on ratios, and by ratio I mean you're just dividing one frequency by another. And so they just extended it, right? So Pythagoras went to 4/3, but later on they just added in 5 over 4 and 6 over 5. But these are the basic intervals that we think of in terms of music. Okay, written music. Written music is actually a logarithmic scale. It is, so I have on here the frequency in hertz. Of course, you don't normally see all of this in the background, but we start off at 100 hertz and then it goes to 700 hertz. So that's really a really short range of frequencies if you think about it. But we can map on the physical scale. So that scale that Pythagoras came up with, it follows this equation here, where the next frequency is just, so you have some frequency, say 110. Then you want the next note in the physical scale, it's going to be 2 times 110, or then 3 times 110. And that turns out to map out all of our intervals. And so the musical staff actually mimics that. So on here, you have, I have it as G on here, but the first between 1 and 2 is an octave, so the next note is a G. And then you go to the fifth and you have a D, and it continues on. You have your fourth, and then your major third, and your minor third, and then the next one does not give anything. It's kind of somewhere in between, a half step and a whole step. But it does follow the scale system. Now, that's not what when we think of like a major scale or a minor scale, that's a little bit different, right? That is the diatonic scale, which is kind of a self-imposed, it was a man-made construct of how these notes should go in order. Okay, getting into some of the music here. So years ago, I wrote a book. Actually, I started it as a play. We tried to make it into a animated story, which did not work out in the end, and it became a book. But we had a lot of advertisement. And so one of the very first pieces that I ever did was for an online, and this is back, must have been 06, 07, that we put this online. And so that's too loud, blowing you guys away. back and listening to some of this stuff, it turns out I'm really into like dark synth. I don't know. It's okay. So another thing that we did with the book was, let me actually go back here and explain. These are the characters from the book. They were Niles and Livy is an oxygen atom and Niles is a nitrogen atom, and they do little atom things. They live in the air in a kitchen. And it was written for kids, right? And the little thing that you see flying around here, that's Ernie the electron, and Ernie is very pesky. And so one of the things that atoms love to do is to play music because they all vibrate. And so if you're going to, want to play music, you're going to play with other people, so you form a band. And so this is the saltwater band. And so we have 2 hydrogens that are going to play drums, right? Because one is never enough. Then you have oxygen on flute, okay? Now, sodium likes to play piano, but sodium can only play 2 notes, right? So the notes that they can play is based on what lines they have. So she brings her friend chlorine along and helps to play. And then you have boron. Now, boron plays bass, right? So if you look at the lines on here, boron's all down in the lower end. There's only 3 lines. If I put the other octave on there, it has 4 notes it can play. And boron doesn't like to stay with the rest of the molecule very long. It wants to flit around. And so I have several bass players in my family, and they all go from band to band to band constantly. So that's kind of where that joke came from. But this is this was done for another project a little later on. Yep.
Station CD 101.9.
Oh, I think I do. Yes. I did. So that really, I did it with the idea of the molecules playing the music, and that was before I actually had the AtomTones actually completed. So that was all done with samples and stuff. Okay, atom scales. So one of the things that I was interested in being able to do was to play music with these tones. And so I took the converted frequencies. So these are the frequencies for the iron lines that we had mapped out. And I compared them to the equal tempered frequencies that what they were. And then I calculated the sense difference between them. So how far off are they from equal temperament? Okay. And so this is the scale for iron. I have done it for every one of the elements. And what's really cool is there are no 2 scales that are alike. They are all different. And, you might have some of the same notes in there, but you do in a lot of the different scales. So, okay. So this is what I did on my COVID vacation. Right before COVID hit, I had the opportunity to I had been working with a group called Ensemble Connect, which is a residency at Carnegie Hall. I had been working with them for quite a while, and we had made an arrangement to do some recordings of some of these scales. And so I had probably 2 to 3 hours worth of improvisational sounds. We just kind of, in my class, we were throwing out ideas and they were playing, and it was all big mishmash. And then I was working alongside a sound designer out of the UK. We were doing some of the granular synthesis stuff. We had gotten some data from the Keck telescope, and then added in the sounds of the AtomTones. And so then we put it through a plugin and created granular sounds from that. And so I did an entire album of this. And this is actually, I did it all by myself, sitting in the living room. I couldn't get out. It was, what better thing to do? So the song that I'm going to play now has a lot of personal meaning. It's called Nitrogen Narcosis. I was a diver for many years. And one time I was under for too long. We had gone down on a very deep dive, and then we came up and somehow ended up going to someplace else. I had too much nitrogen in my system. Nitrogen narcosis is a very narcotic effect. You have too much nitrogen in your blood. And after having a very nice conversation with 3 hammerhead sharks that probably did not exist,
Happy for that.
So anyway, I had stuck my hand in a sea urchin. It was a whole big mess. But anyway, this is what this was mimicking. This is what I was envisioning was going on. And so that's actually how I remember it happening. It was when you're diving, you got like bubbles and it's noisy and everything's going on. And then when the nitrogen narcosis took over, everything was quiet, except for the hammerhead sharks, right? Who apparently talk. Whoops. Okay, one of my dreams going back probably to, probably like 2000, like even the late 90s. I wanted to do an atomic opera. And in particular, I wanted to do a multi-genre atomic opera because I love different genres. I'm not one who wants to listen to the same type of music all the time. I want to switch it up. And so my idea is that I take some of these like cartoon type of things, the Atomville, the Atoms, Niall and Livy and their adventures and stuff. And I don't know, I see the world in cartoons, so I wanted to create a kind of an opera. And so that was one of the things that I had always wanted to do. I had some examples online that I'm not going to necessarily go through all of them, but this is on, again, my website. One of the interesting things, though, this tells kind of the story of how I want it to kind of map out. But one of the things I found was when I first started doing this, I hadn't actually created the atom tones. So which comes first, the chicken or the egg? I had decided that nobles, right, the noble gases should play classical music because they were noble, right? That's what they're going to listen to. Well, as it turns out, when you actually play them and play the scales, they're very jazzy, right? Or blues. I'm sorry, they're very blues sounding in their tones. And so some of them I've had to rearrange, but yeah, someday that'll happen in my spare time. And so there's a couple of samples here from just like student work that we have done and some other people that I worked with and stuff. Oh, now I have to toggle back. There we go. Okay. There we go. All right. So the next part that I want to talk about is kind of a surprise reaction from people on these tones, and that is the mysticism. They're always quoting Nikola Tesla to me, and they always quote it wrong. So I have the real quote here. This is so if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. What he was referring to was resonances and harmonics, right? So everything that we think about with music. I'm going to play a little video here to show exactly what we mean by harmonics and resonance. And we're probably going to get an ad.
Every video production can benefit from the tools to help stabilize
Sorry.
and stylize camera movement.
Okay.
So it's Friday again, so clearly time for some physics fun. What I've got set up here is a vibration generator. So the pin here will move up and down. I have a spring, and that's a spring with a K of about 30. And then I have a 100-gram mass, and I have a second spring attached to a clamp stand that's out of shot. So it's a dead simple experiment to do. We have the signal generator at the back here, and at the moment I've turned down the amplitude. So I'm going to turn up the amplitude, which is hidden, and we're going to put it on maximum, and hopefully you can clearly see that this pin now is vibrating at a frequency of 2.06 Hertz. Now let's see what happens if we dial down the frequency. We're now going at 1 Hertz, well, nearly a Hertz there, 1 Hertz frequency. So up and down, okay. Let's go up a little bit. We'll go slowly, so you can clearly see, getting a bit more motion with that mass. And I've done a scale on the back here, and this is in centimetres, so it's every 2 centimetres. I did a bit of a line at the mid value. Now it's not perfect because I'm on a bit of an angle, but it's not really designed to do an accurate display. We're just looking for an overall effect. So 2 Hertz, pretty much the same thing is happening. So let's go up a little bit more. There we go. 2.5. It seems to have died off now. There's not a lot happening. 2.7, 2.8, 3 Hertz. Oh, interesting. Wow. 3.2, 3.3. Crikey. The amplitude is massive. Looking at least 14 centimetres. Well, let's just go up a little bit more. 4. Oh dear, it's died off. 4.4, 5, 5. Oh, it's gone. That effect has gone. Let's go back. Now, I think it was roughly around the 3 point. There we are. 3.3. We're roughly looking about that. So we're clearly seeing a resonance effect. So what we're actually talking about is that when the frequency of the periodic force applied, so the force that's applied here to the mass spring system, equals what we call F0, or the natural frequency, large amplitudes of oscillation occur. providing the damping is light.
Okay, so I won't make you listen to the rest of it because it gets into the math and stuff like that. But the idea here is that idea of resonance is really how instruments work, right? And how all kinds of stuff actually operates. So we use it quite a lot. There we go. So these are some examples of resonance. So what you're seeing in the picture are what we call Chladni plates. It's just a simple metal plate, and you just put on a signal generator like he had on the video, and you sprinkle sand on it, and these patterns, when you hit into a resonance, these patterns appear. And so it's really easy to do. I do this in my class all the time. The students absolutely love it, and I get sand everywhere. And facilities people don't love it, but
Can you attach the frequency to each one of those?
Yes. And when you're in between, if you're not at a resonant frequency, what happens is the sand just goes everywhere. And then if you go back and you hit into a resonance, and so these resonances follow that harmonic structure, that equation that you saw in the beginning where I said Fn equals n times F1. So these are really predictable frequencies that we can kind of zone in on. And so this idea holds for a lot of our technology. So cell phones operate on this, radio, fiber optics, spectroscopy. Actually, our eyes and our ears work on this, or our own bodies work on this. So this idea that Tesla had is really a useful idea. But what it doesn't do, what it does not mean, is that 432 hertz is the be-all and end-all of all frequencies. I have gotten so much email on, what do you think of 432? Either that or what atom should I listen to cure my cancer? Which I am absolutely not going to get into that at all. Radium. Yeah, there you go. All right, so I did a little research on this to see why 432, what gave them the idea that this was. And so what I was finding was that they were saying that Pythagoras is credited with discovering 432 hertz. They also say it's gives you good luck, abundance of money and prosperity into your life. And then some proponents believe it was a more harmonious and natural frequency compared to the standard concert pitch of 440 hertz. I won't start with the fact that that's, again, a human-made construct. We all agree that 440 is A. There's nothing else to it. Okay, so I had just kind of rebutted a little bit here. While Pythagoras did develop an intricate tuning system, he could not have measured it in seconds, right? Because seconds was not even a unit of time until the 1500s. The idea of frequency is the number of cycles in 1 second. That did not come around until the 1800s. So Pythagoras had nothing to do with that at all. Okay, as far as a good luck symbol, why not? You can use it for anything. I just threw up some good luck symbols up there. And then I did some math. I looked at why do they think it's the natural frequency? Well, this comes from the resonance of Earth that they measure. There is in the ionosphere, and the Earth creates a cavity, right? Just like, like a guitar cavity type of thing. And you get standing waves that set up inside there. They measure them. This is something that's actually measurable at 7.83 hertz. And this is their reasoning for 432. Well, here is our equation. There's that harmonic frequency. This is the one that governs everything. If it is 7.83, okay, then it comes down to, I'm calculating for n, right? So n in the harmonic series has to be an integer. It has to be 1, 2, 3, 4. It can't be 1.5 or 1.76. It has to be a whole number. That's one of the rules for that calculation. So if you do it with 432, you get 55.172. Okay, it cannot be, right? So then I have read online where they said, well, they actually rounded off to 8 hertz. Okay, well, that's fine. Then you could use the 432 and you get 54. But when you round it off, you are actually changing what that natural frequency is. And so I went through and I did the calculations. So this is the equation used to calculate the sense. And when I did that and I figured out what the frequency was going backwards, it turns out that that natural frequency should be, if I round it off, at 440 hertz. So I just thought that was kind of ironic. And that's all I have right now. So,
We do have one or two questions from Facebook besides possibly the audience. And due to the fact that we're using a shotgun mic, whoever wants to ask a question, please come next to Professor Jill and ask it. So on behalf of Brian Knight, does the shape of the plate affect the resonance example's shape or pattern? And obviously yes, but please explain it on a more technical basis.
Absolutely. It's just like with the instrument, right? So I had shown the conical winds. If I had picked a flute instead, or a guitar, or a violin, they're all going to have different shapes, and the shapes are going to dictate where the standing wave patterns appear. And so we think of like these plates as being almost a mesh of lines of masses and springs, and so you end up almost like with a grid, and so they're going to interact together, and the shape has everything to do with it. There's a really nice demonstration or simulation called on PHET, P-H-E-T, that does normal modes, and if you go to normal modes, you can actually play around with different shapes and different numbers of masses and see the different patterns that appear. It's pretty cool to play with.
Cool. John Osborne, either
Can I ask the question? You just repeat
she'll have to repeat it for you.
Okay. So on the periodic table that you showed us, clearly there are different denominations of like alkali metals or the transition. Have you noticed between different elements within those groups, or just even in general, have you noticed a pattern of like which elements have more notes that they like, were they a character they could hypothetically play, or is there any logic or rhyme to that?
Okay, so the question is there any rhyme or reason to the ordering of the elements on the periodic table in terms of the tones? And the answer is no. Actually, there are patterns that are appearing, but they are not necessarily within the alkalis versus the, noble gases or things like that. But there are certain patterns that are like with the decay chain that I showed. So that lead, that stable element, that seems to be more of a pattern that will appear. There are several elements that have very pure tones to them. And I'm not 100% sure the reason why, but the patterns that are appearing are not necessarily matching what's in the periodic table. And so,
Can I ask a second question?
Of course.
Have you noticed when, like, say you have uranium that is decaying, have you noticed any relationship between the element and what it to as like, because obviously it goes more towards a sine wave and becomes more clear, but like, are there any other connections there, or is it just that?
I have not really had a chance to kind of get into it that deeply.
Could you repeat the question for us?
Sorry.
Oh, did I notice any other patterns? Is right? That was the question you were asking. I haven't really noticed too many patterns. We ended up going more into looking at molecules. So most of the work right now is in how to create accurately molecule sounds. And so we kind of went away because we weren't finding any. The other thing we weren't finding any connection to were the harmonic frequencies. None of the tones are showing harmonic frequencies, which is really interesting. I have no idea what it means, but it's really interesting that it's almost like anti-harmonic, right? The sounds, each individual note seems to be independent of it, and we're not seeing any connection in that at all.
Thank you.
Sam?
My question starts with a clarifying. Could you remind me how the scales were derived?
From the tones?
Yeah.
So I took from the diatonic scale system, which says you're going to have a sequence of notes within an octave. So rather than going on the physical scale, if I were to map these out, they would go from below the staff, right, the bass clef, all the way above the treble clef. And so you want to kind of fold them over into an octave. And that was based on how the diatonic scales were originally put together. But then I just took the notes that appeared within that element and set it in order.
In terms of patterns, I thought it was being one note.
Yeah.
It's like very pentatonic, which pentatonic scales sort of have this resonant
Yep.
to them.
I see that a lot, actually.
Especially for guitar players.
Yeah.
Right.
Anyone? I just had an observation. I noticed that iron is 55.8 something, which is obviously a little bit sharp of A.
Mm-hmm.
And is that what you were saying just a moment ago about none of them
And
actually are harmonic tones? They're always a little off.
right. So the what the actual frequency is, that wasn't so much what I was worried about or looking at, but the intervals, right? So going from one line to the next line, you would think that
spectrograph.
in the spec, yes, you would think that we would see at least here and there a perfect fifth or a fourth or maybe even a major or minor third, and they're not showing up at all. We're finding that it's the exact opposite of that.
So maybe Pythagoras has forced us into a system that isn't even natural or
Well, I think
as
the
harmonic as we
mathematics give us this, and we have a lot of success. All of those devices that I was talking about, all of those inventions, all are based on that harmonic spectrum. So it definitely has something there. It's just really interesting that they don't in terms of the atomic spectra.
As an inventor of the equalizer, I'm completely in belief that,
Yeah.
as I frequently say, frequencies are everything.
Yes.
and make a big difference in
Yep.
what we do as audio people. Question?
I have a
Yeah.
Greg?
Yeah.
Why don't you come on up so
Yep.
we can actually hear it in the Facebook?
Yeah, because I think I keep forgetting to say what the question is.
I'll be able to fix all this in post, but
That's
near her because it's a shotgun.
Sure.
yeah.
Wonderful presentation.
Oh, thank you.
So the marriage of math and science and music is incredible. I saw some documentaries on television where they found these older caves that were almost sonically designed. These are ancient caves. But the rooms themselves were designed to create tones and create different sounds through the apertures and the narrow pathways of the cave. And then you also mentioned your experience underwater, which is where you were, again, I understand why it was created because of the lack of oxygen to you. I guess my question is there... This is from the periodic table, and this is from elements that exist on our planet. Are there any circumstances where these, instead of being done through software or things like that, that this can actually be produced physically in the physical world?
The answer is I have no idea. There are certainly, each atom has its own resonances, and so different materials are going to resonate differently. So certainly if you think of how marble, right, resonates a whole lot better, right? So if you have a marble room, you get lots of resonance going on in there,
Right.
and you have a room like this, you shut the door and I'm like, oh, this is an awesome space.
Yes, it is.
But you don't get that resonance in
No.
here, right?
Yeah,
You don't get that reverberation, right? And so
that costs a lot of money to go
yeah,
something like that.
but you paid. So in order to get that response, you paid very careful attention to what you put on the walls.
Environmentally,
And,
right.
Yes, right. And so we can control the environment in terms of the different atoms, the different materials that we use. This gets into the molecules, which
Yeah.
is where I'm working now, which changes things because when atoms bond, right, they're sharing electrons. So it changes the way that they
Right.
vibrate. And so we have to actually look at a different way that they're being produced.
Right. I guess
And
based
so-
on, really my question was based on elements, right?
Mhm.
And this is all coming from elements and atoms and science. Environment.
Mhm.
Does taking these tones that you're creating from the elemental factors into other environments like underwater, like different areas, would they produce obviously different sounds?
I would think so, but I've never tried it myself.
Right.
So I've never actually done the experiment on that. But I was actually thinking about that, especially with like underwater. How would that sound underwater? Or
Right.
how would it sound in a different environment?
Right.
What would it sound like in here versus in a gym, right? Where you have lots of
Different
reverb going on.
Exactly.
Yeah.
Or those
At that point,
caves.
it's ambience. Like it
Yes.
is
Right.
Yeah,
music.
exactly. Exactly.
The
Mhm.
source is
The source is the same.
natural,
Right. Mhm.
elemental
Right.
Yeah,
part of it.
absolutely.
Thank you.
Right. You're welcome.
Great place, Greg.
Thank you, Roy.
By the way, Greg's the owner.
Yeah. Oh, I'm glad I said something nice about your room here. I do really. That door closed, and I went, oh yeah.
Did you say you had recorded like a whole album?
Yes. So it's on the website, which is AtomTones.com. Yeah, there are 5 different pieces, and there's also another album that I did. Well, actually, really more. My student did it, but we worked together on that. And so that's called Simorphic, which is an homage to different synthesis types. So.
Just a little technical side note that Jill has recently updated her website and is in the process of resetting up her downloadable sounds. Before she had done that, I had visited the site and was able to download a tone that has become my ringtone for my notifications for my messages. And it's very sonic sounding. Denise and I used to have the same Star Trek sound, but now I've gone my own way with Atomic. You're still cool again.
Yeah.
So that's Denise Barbarito. Just make sure everyone can find you. If there's no other questions in the audience, and let me double check that there are none in our Zuckerberg land. Does not seem that any have come in addition to the ones I asked. Okay, so as I said, we'll be reposting this with some post-production, and it will include some of the video that you weren't able to see when you were watching, and it will be archived in Facebook Live until the 30 days go by, and then it'll be on our YouTube, so feel free to come back and check it out, and it'll be a little bit more detailed than what we streamed out to you at that given moment. So thanks all in Facebook for joining us. We're going to end the stream, and in a moment we're going to have our Eventide audio raffle for the audience attendees. And just think about it. If you come to our events, there's that wonderful chance to network with people, to be in a cool facility, to hear and see some great content, to win a raffle or two. So it's a good thing to do. And the next one is on April 22nd at VoxPod/Buttons Studio, and it'll be 50 years of audio, Saturday Night Live, then and now. So thanks everyone for coming, and let me just tell them to stop the stream.
Well, thank you guys for all listening. Oh. I have so many ideas of things I want to do with this. All I need is time.